this in our forefront of our brains, this will get us to it. All right, so what are we dealing with? So the problem is we have this Lie group here, which I guess now I am drawing like a group for black and red for topology, and we'll call this group. Let's call it A1 because I'm immediately going to draw another group, which is different from A1, but it's still a Lie group. And we'll call this A2. So we have these. I've drawn four, but there's no reason to be only four. So I'll label them A1, A2, A3, AN. So it'll be N of them. And then we presume that there's a Lie group out there, or I'm sorry, Lie algebra out there, which I'll draw with a script A. Oops, I have trouble with script A's. I've had trouble with script anything. Hold on, I can do this. I can do a script A. I'll do it real big. Up, down, around. Oh god, that's terrible. Hold on. Okay, fine. That's a good script A. And this Lie algebra is the Lie algebra associated with each of these different Lie groups, right? In principle, this can happen, right? You can have a whole number of Lie groups out there that all share the same Lie algebra, and the process is linearization. So now the obvious question is, okay, all of these Lie groups, they're different groups, right? They're different groups, different topological spaces, yet when they're linearized, they all produce the same Lie algebra. And by the same Lie algebra, we mean that the commutation relations are ultimately the same. So what gives? What's the relationship between these guys that yields the same Lie algebra? And then the problem is, if you started with just a Lie algebra and no information about any groups, and you exponentiated, you could invert any of these paths, and you can create multiple different Lie groups through exponentiation. Therefore, exponentiation is not unique, right? Linearization is in fact unique in the sense that I start with any given group and I linearize it. I will get a unique Lie algebra. I can't screw this up. But starting with Lie algebra, you have different choices of which group to land in. So how do we clean this up to understand all of these relationships? Well, the first thing we start is we look back here on this page. Every group has a fundamental group, right? I'm looking at the fundamental group of the Lie group, right? Notice that there's no fundamental group of the Lie algebra. There's a fundamental group of the Lie group. So each of these Lie algebras has a fundamental group, and let's put that in there. So this would be, for example, pi1 of A1, and this would be pi1 of A2. So now each of these fundamental groups has a Lie algebra. Each of these Lie groups has a fundamental group. Well, in this situation, when this is in this condition, when this happens, and we look at each and every one of these Lie groups that produces a Lie algebra, one of them is going to stand out, and it's going to stand out in the following way. One of them is going to stand out because its fundamental group is going to be trivial, right? When I say a fundamental group is trivial, what am I really saying? If I write the fundamental group is trivial, that's saying, first of all, it's saying that all paths in that group are homotopic to the constant path, which is saying that the group is simply connected. And that's the important point. The important point is that only one of these groups will ever be simply connected. If you find two that are simply connected, that means they are homeomorphic, meaning that they're isomorphic as groups and they're homeomorphic as topological spaces, right? So, and they're not homeomorphic because they're both simply connected. Let me make that clear. But in this context, if I find two Lie groups that share the same Lie algebra that are both simply connected, then I'm really looking at the same Lie group, and I need to eliminate one of the two. They're basically, as far as groups and as far as topological spaces go, they're the same. I want to make it really clear that groups that share the same fundamental group are not necessarily homeomorphic. In this case, they will. So, those groups essentially only one of them is simply connected, and that group is particularly important. So let's indicate that by, let's call A3 that group. So A3 is the simply connected Lie group. Then I'm going to mark that in purple, and we are going to take that simply connected Lie group, and we are going to elevate it above the others. Above the others, because it is better than the others. And then I'm going to erase these, and I'm going to redraw these lines like this. Right, it's still like the same. It's still the same in every other way, right? In other words, it uniquely linearizes to the algebra. But now I can say that this is unique. This is the exponentiation now is unique. And it's unique in the sense that any given algebra, there is a unique exponentiation to a simply connected Lie group. That is to say, if I start with the algebra and I want to find a simply connected Lie group, there's only one exponentiation that will derive from the same connected groups. It's certainly not unique for all these groups, because that would be all of these groups, right? If I consider all of these groups, it's not a unique process exponentiation. But if I just consider simply connected groups, then suddenly it is unique. So I don't think the word unique in there for that reason. And I guess the last step I'm going to do is I'm going to I'm going to clean up this in here because it's no longer vague, right? So I'm going to write down pi 1 of A3 equals, and I'll just put the set with the identity in it, right? Because that's the definition of being simply connected, right? If your fundamental group is trivial, then you're simply connected. But all these others, we don't know what their fundamental group is. But in this case, it's the identity. All right, so now that we have this, now we go back to, all of these things that we know about our Lie groups, which I'll do on the bigger screen here. So there are other facts that we know. We know about the connected component, but we know about these discrete invariant subgroups, so that's interesting. So these discrete invariant subgroups, that's now where we're going to turn our attention, right? We're going to turn our attention to the discrete invariant subgroups. So the first thing to remember is, let's look at this guy. This guy is simply connected. So as far as sheets go, this guy has one sheet. So G0 equals G. So I can write that in there. G0 equals G, right? And then I presume that there's a bunch of discrete invariant subgroups there. So I'll list the discrete invariant subgroups right here. So remember, I put them outside of all of this stuff to show that it's related purely to the group structure. But they're discrete invariant subgroups. And this group is simply connected. Now, there is an important thing you need to know about discrete invariant subgroups when you have a group that is simply connected. And the idea is, if these are invariant subgroups, we can actually say a little bit more about them than just the fact that they're invariant subgroups under this condition. And let's cover that real quick. So let's remember the rule. The rule is, if D is a discrete invariant subgroup of the set A3, then any member of the group, I'll call it G multiplied by D using the group operation has to equal the multiplication from the other direction. It has to be equal. And so remember how this works, right? G is an element of the group. D is not an element of the group. D is actually a subset, a subgroup of the group that has this property of being an invariant subgroup. The property of being an invariant subgroup is satisfying this. So I'm saying G times a subset. So what does that mean? Well, basically, the way to think about that, I'll remind you, is G group operation on the set of all elements D0, D1, D2, Dm, right? This is going to equal another subset, the subset of G times D0, G times D1, G times D2. Those are all group elements, and this is now a new subset of the group. Now, if D is an invariant subgroup, then this set here is going to equal the set where G and D0 are all reversed, right? Which would in principle be different elements if it's a non-commutative group, which most of the interesting ones are. So that property is what makes it an invariant subgroup. Another way of thinking of it is this is the left coset of the subgroup D, and this is the right coset of the subgroup D. And if the left and right cosets are the same, you're dealing with an invariant subgroup. Another way of looking at it is G, D, G inverse equals D, right? That's another way of looking at it. So those are that would be a generic discrete invariant subgroup. What's important to understand, though, is that this is a simply connected group, and it's a continuous Lie group. So in there is the identity element, and any element G can be slowly brought to the identity continuously. So if I look at this definition, what I can see is, say I take one given element out of D, and I write it as G group operation D, say D alpha, just pick some member of D, group operation G inverse. That has to be equal to another element of the discrete invariant subgroup, right? So I would write that as D beta. But that's always got to be true. But now I continuously let G move towards the identity, right? So I end up with the identity D alpha. The inverse of the identity is the identity equals D beta. And what I end up with is D alpha equals D beta. And what this tells me is that in the circumstance when you can continuously move G very slowly, such that this is always true. Remember, it's the point being that D alpha, D beta are discrete. This is where discrete comes in, right? This is where the discreteness comes in. Because, discrete or discrete? What does this one mean? Wait. This one here with two E's, that means being cautious or being subtle. And this one means particle. Yeah, this is the discrete. I mean, with EG. But anyway, so the point is, in order for this to continuously move, and for A and B to discretely move, the only way that can be is if DA equals DG, right? That's very important to understand. I slowly and continuously move G towards the identity. I always maintain the same discrete element of our discrete invariant subgroup. So if it's spread out equal DB, and I make these changes, and I don't change this, DB would have to change. But DB has to change abruptly. So for this to be a smooth transition, the only way to be the case is if DA and DB are the same. And the reason this is important is that if that's true, then what you have is for every element, you have GDA equals DAG, right? This, you just move this G to the other side, and the bottom line is that every element of a discrete invariant subgroup of a continuous group that is simply connected, the simply connected part is allowing us to move from any element G to the identity, right? So you need to be simply connected for this to work, a continuous group for that to work, obviously, although so the two are very related. And it has to be a discrete invariant subgroup. If it was indiscrete, then Delta dB could in principle adjust itself to make this always true, but it can't adjust itself, it has to abruptly switch. So for a discrete invariant subgroup of a Lie algebra, every discrete invariant subgroup commutes with every element of the group. So all of these discrete invariant subgroups are actually are elements that must commute with every element in the group. Okay, so now we know that. We now can go back to group theory again, right? And we can talk about the center of part of A3. And the center of any group is the set of all elements that commute with everything in the group. And every group has a center, maybe even true, but if it's not, then the center can be an interesting subset of the group A3. But it's not just a subset, it's actually a subgroup, so the center is a subgroup. And in fact, because everything commutes with the center, it's also an invariant subgroup, right? So if we look at the center of A3, right, all of the elements that commute with everything in A3, then what we would discover is a center group, which we would call, well, I'll call it just D, because we're kind of committing ourselves to D. So D is the center of A3. Now, if D1 and D2 and Dn, if those are all discrete invariant subgroups, we know that they also commute with everything in the group. But they may be smaller than D. D is the largest collection of elements that commute with everything in the group. So D1 must be a subset of D, and D2 must be a subset of D, and Dn must be a subset of D. So the point is if we can look at the simply connected group, find the center, and then look for all the subgroups of the center, then we will have found every discrete invariant subgroup of our simply connected group. Right? That's what's so important. Finding the center of a group isn't as tough an exercise. And once you find the center of the group, well, that's a subgroup. Now you study it, and you look for its subgroups. And these are now discrete groups. These are like your elementary groups from your first year of studying group theory. Right? Remember things like this, right, where we had group tables from discrete groups? This is what discrete means, right? It's a finite collection or a countable collection. I guess discrete means countable, but these groups are typically the ones we work with are finite groups, just like the ones we've always studied before. So now we use all the properties of the simply connectedness is what demanded the commutativity, which gives us the center. The center then gives us these discrete invariant subgroups. So by finding this one simply connected, which is guaranteed to exist, right? We haven't proved it yet, but it's guaranteed to exist from the Lie algebra. This is very important exponentiation to find the Lie group that is simply connected and has these discrete invariant subgroups that are all subgroups of its center. Okay. So I guess we should add the center to this story here. I'll call it D. That's the center. We'll add that to our list of things to keep track of. Okay. So now I think we're finally in a position to get to the bottom of all of this relationship. Knowing all of these facts about the simply connected group, that was the key. So now we want to find out what is the relationship between A1, this Lie group, who shares the same Lie algebra with this special magic simply connected group. What's this relationship? And the relationship is pretty simple now that we've gotten all this construction done. The connection here is that A1 equals the factor group of A3 with one of its discrete invariant subgroups. A2 is equal to the factor group of the simply connected group with the other discrete invariant subgroup. An is A3 over whatever remaining discrete invariant subgroups are out there. So there's going to be as many of these Lie algebras that share the same Lie group as there are discrete invariant subgroups of the one unique simply connected group. And this simply connected group, now I can finally say it, it's called the universal cover. And the universal covering group, it's the grand group that covers all of these groups. And we can, once we know it, and once we understand its center, and then we study its center and get its discrete invariant subgroups, we can quickly derive every Lie group that shares the same Lie algebra. So the things that you have to get your head around in order to really feel this is you have to be able to say in your mind, oh, I understand what the factor group would be of a simply connected continuous group by a discrete invariant subgroup. This notion of a factor group has got to mean something to you. And the only way it can mean something to you is if you understand that a discrete invariant, I guess the way I should say is, an invariant subgroup can create a factor group through this process of creating all of the cosets. So this process here means A1 is a Lie group that is isomorphic. I guess I should say that this is isomorphic, right? It's isomorphic. I guess that's true for all of these, right? Isomorphic. It's isomorphic to the factor group A3 by D1. And the factor group A3 by D1 is the set of all cosets, right? Remember how that works? It's the set of all cosets of the discrete invariant subgroup. So A1, so say I wanted to create A1, right? So I take, in our case, A3, right? And then I take D1. Then I pick out an element of A3, which I'll call, say, A, and I form the set A by D1, which is a coset, right? It's going to be A D0, A D1, all the way to A Dn, right? So I'm going to have a set that contains A, some arbitrary element pulled out of A3, multiplied by the entire discrete invariant subgroup. This will be countable, if not finite. In fact, in all of our circumstances, I think will work. This is going to be finite, right? So finite number, say, of elements in this coset, and that is the coset of A by D1. And it's the left coset. But I don't have to worry about the right coset because D1 is a normal or invariant subgroup, so these two cosets will end up being the same. They'll be generated in a different order, right? It'll be D0A, D1A, DNA, but ultimately the set will be the same. Now, this coset does not have to be a subgroup, it's just a coset. But the point is I create that coset, right? I create that coset, and I throw that coset into a bin, right? I'll call that the coset of A, right? And then I pick another element, I pick B, and I create its coset, and I put it in the bin. And then I take an element C and I create its coset and I put it in the bin. Right? And so this bin contains the cosets for every element of A3, right? All of those cosets. Now some of these cosets will turn out to be the same, right? In other words, I'm going to go into A3 and I'll pull out A and I'll get this set, and that'll be the coset of A. But then I might take another element of A and discover that that's equal to this element of the coset. And then it's going to generate the exact same coset, right? That's how this all works, right? That's how cosets work. They partition the set. So that will end up being the same coset. So I don't repeat the coset, right? The coset representative, I pick one representative, and that will be A. And A will always be part of the coset because D1 is a subgroup, therefore it has the identity. So one of these elements, probably AD0, will actually be in the group. Likewise, when I pick B out, B will be in this coset. So anyway, the point is I have a group that's somehow smaller. It's smaller than A. I mean, there's still an infinite element of A, and because this is discrete, there's going to be an infinite number of cosets here. But I've created this set of cosets, and I know how to do group operations on cosets, right? What's the rule? Right? So if I'm going to turn this set of cosets into a group, I need a group operation. Well, the group operation is a coset represented by A, group operation in here, a group operation in this set, times a coset represented by B is going to be the coset represented by A group operation B, where this group operation, right, that group operation comes from A3, So I guess you should even give this a little different color because it's a different group operation. So with that, we are guaranteed that this, because D1 is a invariant subgroup of A3, we're guaranteed that this will be a group. And what I'm trying to explain today is that that group is going to be isomorphic to a Lie group who shares the same Lie algebra. And in this case, that Lie group was what we were calling A1. And the reason was because we chose the D1, right, corresponding the first discrete variant subgroup with the first of these Lie algebras. So that is the magic. That is the magic that makes this all work. So what I was trying to do there basically was make it so this doesn't seem intimidating. The fact that this is just this set of cosets, or it's isomorphic, right? It's isomorphic. However we describe A1, we can always put it into one-to-one correspondence with this set of cosets. Isomorphism is what makes this abstract algebra and what makes this topology abstract. Right? These isomorphisms, everything up to isomorphism is the same for groups. Everything up to homeomorphism is the same for topological spaces. So for every discrete variant subgroup, we can do this. We can do this, and we can get and capture each of these groups. All right. So that actually, that's mind-blowing enough, right? But the next step is the one that really is mind-blowing because appreciating it really shows the deep connections here in the mathematics. But you'll notice that the fundamental group was important to us. The fundamental group of these different Lie groups was important to us because we wanted to find this guy. We wanted to find the one that made it the fundamental group that was trivial because we were looking for the simply connected Lie group, which we were going to identify as the universal covering group. By the way, I know I haven't proven all of this stuff. That's going to be for later lectures. But I want you to see the facts that are kind of amazing, and hopefully you'll want to see the proofs because it's almost like it's hard to believe, right? Why should this be the case? So we're looking for the universal covering group, and that's why we dig through each of these fundamental groups until we find the one that has the simply connected property. But what's really interesting is that A1 does not have the simply connected property. This fundamental group is not trivial. Neither is this fundamental group. Neither is this. If any one of these fundamental groups were also trivial as well, that would mean that A2 was isomorphic and homeomorphic to A3. Again, with the caveat, it's not homeomorphic because they have the same fundamental group. In this context of Lie groups, that is true. The point being that there's only one unique Lie group that is simply connected, right? I've said that over and over again. But what about these? Have we wasted our time calculating these, right? If I laid out all n of these, and I calculate this, and it's not trivial. I calculate this, it's not trivial. Oh, I got to the third one, it was trivial, so I'm done. What about all of the other fundamental groups? Do we care anymore? But the way I've said it so far, no. But the fact that is really mind-blowing here is that if I go and I now look at, say, A1, I've got A1 is isomorphic to the factor group of A3 by its discrete variant subgroup D1. The unbelievably interesting fact is that the fundamental group of A1 is isomorphic to D1. And that is true for every one of these. The fundamental group of AN is isomorphic to DN. And that's what takes a moment to sink in. We can study the simply connected group, find its center, right, and then look at all the subgroups of its center and find these discrete groups. Notice that that's a very group-oriented process. The center is going to be discrete, and its subgroups are going to be discrete. But another discrete group that's associated with continuous topological spaces is the fundamental group. And A1's fundamental group is going to mimic one of the discrete subgroups of the universal covering group. And this connects just a purely topological property of this Lie group with a very groupy property property of the universal covering group. So there's the way this is all constructed and bound together, right, all of this stuff that binds these things together, which is a lot of stuff. I mean, when you look at it, you see that you've got continuity conditions, you've got group conditions, you've got the fundamental groups, you've got connectivity conditions, you've got a manifold condition, and then this is an algebra. By the time all that's bound together, the topology of the group theory is so bound up that you can find something through a pure topological analysis on this Lie group, and it ends up being isomorphic to a discrete invariant subgroup in a totally different Lie group that is connected through this process. And that's really the kind of amazing thing. That's really mind-blowing thing here. All right, so when I noticed that the first time, like I think I may have mentioned this in a previous lecture, that it just really impressed me. I really felt like I was beginning to understand why a good understanding of deep mathematics is just fundamentally interesting in and of itself. It's just a really, really interesting concept. Now,